Hi, it's Mr. Anderson, and welcome to my podcast on Gibbs Free Energy. Whenever I get to Gibbs Free Energy in the year, I can see my kids' eyes gloss over and they're confused. And even William Gibbs talks about this in this quote. He said, "The idea of entropy and the second law of thermodynamics will seem far-fetched and may repel beginners as obscure and difficult for comprehension." So what does that mean? I'm going to try to tackle something that's been a problem for years. I'm going to try to make Gibbs Free Energy more understandable, and so that you really know what it is and understand the power of it, especially in biology. And so I think the first place to start is the name itself. The idea of free kind of gets in the way. And so what I'd like to go back to is the old name, which it used to be called available energy. And so let's think of delta G as available energy, or energy that we can actually use to do work. The other thing that I think makes it hard is the equation itself is confusing. We've got delta G, we've got enthalpy, we've got entropy, we've got words that you're maybe not understanding. And so what I'm going to try to do is pare this down to the easiest explanation that I can, and then we can get into the more of the specifics a little bit later. And so the best place to start when you're trying to understand available energy or free energy is to look at spontaneous reactions. Spontaneous reactions are reactions that once you give them a little bit of a push, they'll actually go on their own. These reactions also will tend to release energy, and they give energy to their surroundings. Quintessential example in life is cellular respiration. But let's not get there yet. So the three reactions that I'm going to talk about here are, number one, a ball rolling down a slide. Number two, diffusion. And then number three, a cherry bomb that's exploding. And so we're going to apply Gibbs free energy to each of these. So let's start with the ball at the top of the slide. And the ball at the top of the slide is going to roll down to the bottom. And so the first thing that I want to give you is what's called enthalpy, or total energy of a system. And so if we say this is a system, what happens to the total energy of the system as the ball rolls down the slide? Well, if you know anything about potential energy, the amount of potential energy that we have up here is going to be greater than the amount of potential energy that we have down here. And so the total energy of the system, we'll call that H, or enthalpy. The total energy of the system has gone from a big H to a little h. In other words, the total energy of the system has decreased when the ball rolls down. Now, if I had to push it up again, then we would add energy to the system. But this is a spontaneous reaction, and the enthalpy, or the total energy, is decreasing. Now, in biology, we don't move around because of potential energy or mechanical potential energy. In biology, our energy, or our potential energy, is actually in these bonds. In other words, there's a huge amount of potential energy in this bond between the carbon and the hydrogen. And so this right here is glucose. And if we can release some of that energy, we can do it to do work. And so again, what is H? H stands for the total energy of the system. And it looks like in a spontaneous reaction, that's actually going to get smaller or decrease. Okay, next one, let's talk about diffusion. So in diffusion, imagine that right here we've got a bunch of molecules in this container and they're bouncing around, and I remove this wall. So if I remove that wall, what's going to happen to the molecules? The molecules are going to spread out to fill that area. We call that diffusion. Now entropy is, we use the symbol S for that. Entropy is a measure of the disorder of a system, or sometimes we call that the randomness of the system. And so let's compare this. Right here we've got a bunch of molecules on this side, and then we've got a lot of space over here. So what happens to the disorder of that system as I do diffusion? Well, it's becoming more disordered. In other words, the entropy is increasing. What's an example of that? Let's say I go into your room and your room's a mess. It looks like this. If I say clean up your room, then you could go like that. And so what happens through diffusion, or in this spontaneous reaction? Well, let's say remove this wall. What's going to happen now? We're going to get even more disorder. So we're going to even get a bigger S value. And so in this spontaneous reaction, it looks like the S value is increasing. Okay, the last one is that cherry bomb. So let's say we have a cherry bomb. We put it on the desk. Does it explode? No. And one of the reasons it doesn't is the temperature is really low. And so let's say I add a bonfire to the situation, so I increase the temperature. Does that make it a more spontaneous reaction, or is the reaction more likely to happen or less? Well, it's more likely to happen if I increase the temperature, more likely to get an explosion. Okay, so those three things, total energy or enthalpy, entropy or S, and temperature can affect spontaneous reactions. And so now let's apply that to Gibbs free energy. And so before we actually get to the equation, let's just do a little algebra here. So let's say I wrote this equation, x equals y minus ab. Okay, so let's say we had this equation right here, and I were to decrease this value, the y value. What would that do to the x value? It would decrease it, right? Let's say I were to increase the a value and increase the b value. What would that do to the x value? Well, since we're subtracting right here, that would decrease it as well, or make it even go farther down. And so let's go back and summarize those three spontaneous reactions. In the first one, the ball rolled down. So what happened to our H value? Well, our enthalpy of the system decreased. What should that do to our Gibbs free energy or available energy? It should decrease that value. What happened here when we increase the entropy of the system or increase the delta S? Well, if we increase the delta S, that should also decrease the Gibbs free energy. So now we have two things decreasing that. And what happened here? Well, if we increase the temperature, that made it more spontaneous. So if we increase that, we also decrease the Gibbs free energy. So what's the moral of the story? Moral of the story is that if the delta G ever decreases, or if it's ever less than 0, that's a spontaneous reaction. Likewise, if the delta G is greater than 0, let's turn to the next slide, that's going to not be a non-spontaneous reaction. Okay, so in summary, if the delta G is less than 0, that's a spontaneous reaction, or we call that an exergonic reaction, or an energy-releasing reaction. If it's greater than 0, that's an endergonic reaction. And then finally, if nothing happens to the available free energy, then it's just at equilibrium. The quintessential example of a spontaneous reaction in life is going to be cellular respiration. Photosynthesis is an example of an endergonic reaction. And so let's talk about each of those. So let's say we're doing cellular respiration. So what I said earlier is that glucose has a certain amount of energy within the bonds. And so let's do cellular respiration. So I take in sugar, my body is going to combine that with oxygen, we're going to convert that to carbon dioxide and water. So let's animate and see what happens. Wow, so a lot of stuff happened. So let's go back. So first of all, let's look at the entropy of the system. What happened? Did it become more or less ordered? Seems like it became more random, for sure. What happened to the enthalpy of the system? Well, we're releasing energy. So we have energy out here, so we've released energy. That means that the total energy that was contained within those bonds has actually decreased. And so you can look at the value right down here. The delta G of cellular respiration is negative 686 kilocalories per mole. That means if you had about 1/3 of a pound of glucose or sugar, you were to break that down in your body, you would release about 686 calories, big C, of energy. So we call that an exergonic reaction, or it's releasing energy. Now we can actually plot that on a energy diagram. So glucose itself had a certain amount of free energy to start with, but in this cellular respiration, we end up with less energy. So this is a spontaneous or an exergonic reaction. Now, it doesn't just explode into flames, the sugar that's sitting on your counter or the sugar that's inside your body. And so in order to get that to work, you have to put a certain amount of energy into the system. And that amount of energy we call activation energy. And so if you look back to the first three examples I gave you, the ball just didn't roll down the slide on its own. You had to push it. And the cherry bomb just didn't explode on its own. You had to add a little bit of energy to that. We call that activation energy. But there's a net loss in energy. And so we call that an exergonic reaction. Let's think about photosynthesis. What do you need for photosynthesis? Really only three things. Carbon dioxide, water, and sunlight. Oh, four things, because you also need plants. And so in photosynthesis, what happens? Well, we store that energy in glucose. And so if we look at our delta G value, it's a positive, or we call that an endergonic reaction. If we were to actually draw the energy diagram of that, we have a lower amount of energy to start with. a greater amount of energy at the end. And so we're storing energy, and then it has more energy at the end in the form of that glucose. Now, where do we get the activation energy? In photosynthesis, we get that from the sun. And so those two reactions, releasing energy and storing energy, allow life to exist. But our day-to-day life doesn't use glucose, or we do use glucose, but our second-to-second kind of a functioning doesn't use glucose. We actually use something called ATP. And so ATP, or adenosine triphosphate, is the energy coinage of our cells. It's what you're using right now. We can store it as energy, and then we can kind of cash it in. So let me show you what happens. ATP is broken down into ADP, and it releases a certain amount of energy. If we look at that, the breakdown of ATP to ADP, or adenosine diphosphate, it only has two phosphates right here, plus a phosphate group, is a exergonic, or the delta G value is going to be negative. If we go back and convert that ADP back into ATP, now you can see right here that our delta G value is actually positive. Or if we break it, we release energy, and then we can store that again when we make ATP again. And so right now, when you move your finger like this, what's actually powering that muscle is ATP releasing energy. It allows that muscle to contract, and then we can do that over and over and over again. And so you use respiration to get energy, but we actually store that in ATP over time. So what is the secret of life, and how does all of this work? Well, energy comes from the sun. So we have a certain amount of energy up here, and we store that energy through photosynthesis in sugars. And so the release of energy by the sun, the delta G is going to be less than 0. It's an exergonic, or an energy releasing reaction. But photosynthesis is going to have a delta G value that is greater than 0. In other words, it requires energy, and it pairs that to the energy coming from the sun. Next, we make bread out of that, and then through cellular respiration, we are going to release energy. So the delta G value now is less than 0. We use that to store ATP. Now that ATP is used to break down into ADP, and so that's going to be a delta G value of less than 0, and that's going to release energy. But to convert that ADP back into ATP, it's going to be a delta G value greater than 0. And so available energy and free energy is super important. It's converting energy in the sun eventually into energy that we can use, and eventually that energy ends as heat. So the energy is converted that whole way through, but it just becomes more and more disordered as we get to the end. And so that's free energy, and I hope that's helpful.